Alright, welcome to episode 21. If you've been watching this series from the beginning and remember the first episode, you may remember that one of my goals for this 8-bit computer system is to have a display that would be suitable for running the kinds of programs that you would run on a home computer, and specifically a 1970s or 1980s era home computer. So I would like the ability to display text characters. It would be nice if we could have bitmapped graphics and sprites. Definitely it would be nice to have this display be colorful. And so in this video, I will consider various possibilities for how to add such a display to the system, and I will evaluate the possibility of generating VGA output using an FPGA, and I think this may wind up being our best bet. So as I see it, there are essentially two plausible options for generating display output from our 8-bit system. One option would be to use a vintage display integrated circuit such as the TMS9918A, and the other plausible option would be to use some kind of programmable logic such as an FPGA or CPLD. Of all the vintage video display chips, the TMS9918A is probably the most plausible one to use. It has a pretty good set of features. It will generate text, it generates bitmapped graphics, it has sprites. It is definitely an authentic part. It was used in the TI-994A home computer. It was also used in the MSX series of computers that were popular in Japan and Europe. However, it has some pretty significant disadvantages. It's obviously not in production anymore. It's going to be hard to find. You will only find used parts available that were salvaged from systems that were essentially e-waste. It's known to be fairly unreliable. It runs hot. It fails. It's pretty complicated to add video memory to this chip. It was designed to use dynamic memory. I really do not want to use dynamic RAM in my system. And another big disadvantage is that it is composite only for video output, so you will need a CRT or other composite monitor to actually display any video from this chip. Another popular approach for adding a display to a home-built system is to use a programmable logic device such as an FPGA or CPLD and have that generate the display output. And there are a couple of really significant advantages to using this approach. It's very flexible. Because we are actually creating a hardware description, we have total flexibility in terms of how we actually generate the display output. That means we can generate signals for a modern display standard such as VGA, meaning we could use any VGA monitor as the display device for the system. There are two potential objections to using a programmable logic device to generate our display. We could certainly argue that it is not authentic. Certainly, there were no FPGAs or CPLDs that were used in 1970s or 1980s home computer systems. Another potential objection is that we are going to need to actually develop the hardware description for our display device. We will have to use, for example, Verilog to program this FPGA so that it knows how to be a display processor. Here is how I would respond to these two downsides. As far as authenticity is concerned, I am going to imagine that the hypothetical company that created this home computer system had their own hardware fab and created their own custom ASIC that generated the display output for the system. So in that sense, I think we can consider this to be an authentic approach. With regards to the objection that putting a display processor in an FPGA obligates us to develop a hardware description, I think that's actually a really nice learning opportunity. I've been meaning to learn about FPGAs for quite some time, and this is a really good application of an FPGA, so I am excited about learning enough Verilog to create this display processor. Alright, so let's talk a little bit about what FPGAs are and also why I have chosen to try the Upduino 3, which uses the Lattice ICE40 FPGA. So an FPGA is a programmable logic device, and essentially it's a whole bunch of gates and flip-flops that are just sitting on the chip waiting to be configured into some digital circuit. It also contains some number of specialized hardware units, things like adders or comparators. There's often memory on an FPGA and other kinds kinds of specialized components, and there is a routing fabric that essentially allows you to connect them together to form any digital circuit that works with the particular types of hardware that the FPGA has. And then it is possible to route signals inside the FPGA to I/O pins so that your FPGA can react to signals in your circuit and also produce signals that will be sent to your circuit. So let's talk about why I've chosen this particular FPGA dev board, which is the Upduino 3, which uses a Lattice ICE40 series FPGA on it. So the Lattice ICE40 series is reasonably powerful. They are certainly not high-end FPGAs. They're actually fairly low-end, but it should be powerful enough for the application that we are going to be developing. It is quite inexpensive. I think this dev board, the Upduino 3, was about $30, so that's really not too much for an FPGA development board. It has a reasonable amount of memory on it, 15 kilobytes of dual-ported block RAM and 120 kilobytes of single-ported RAM, and this should be useful for things like registers and palettes and fonts, and then the larger single-ported RAM should be good for the frame buffer. The most amazing thing about these Lattice ICE40 FPGAs is that there is an open source toolchain that allows you to develop for them. Essentially, you write your logic description in a hardware description language, specifically Verilog, and the IceStorm toolchain converts the Verilog description into the FPGA-specific binary bit stream that configures the internal hardware on the FPGA. The way the FPGAs work is that before an FPGA can do anything useful, the bit stream that encodes its logic functions needs to be loaded into the FPGA, and that essentially turns the FPGA from this generic reconfigurable hardware into essentially an ASIC to support the needs of the circuit that it is being used in. Most FPGA development boards actually have a flash memory chip that stores the bit stream, and then there is a microcontroller that loads the bit stream into the FPGA when the dev board starts up. There are a lot of reasons why it is so nice to have an open source FPGA development toolchain. Certainly it has all of the benefits that open source software normally has, which is there is a community, there are no licensing costs, you can have complete confidence that you will be able to use the software in the future regardless of whether there is a vendor or authors who want to restrict your access to it. And for FPGA development specifically, the vendor's proprietary development tools often have very problematic aspects. They are going to be licensed in a very restrictive way. They may not run on the system that you want to use them on. They may not be supported indefinitely. So it's really, really nice to have open source tools to do your FPGA programming. So it's just amazing that IceStorm exists. Alright, so that's definitely enough yapping about FPGAs. Let's try to get our FPGA to actually do something at least a little bit interesting. So here is my initial Verilog file, and I am going to use the internal high-frequency oscillator, which oscillates at 48 megahertz. What I'm going to do is divide that frequency by 8 and simply generate a square wave of that lower frequency. And the way that I will do that is I have instantiated a 16-bit counter on every positive edge of the high-frequency oscillator signal. I will increment the counter by 1, and by selecting the third bit of that 16-bit counter, I'm effectively dividing the oscillator frequency by 8. Alright, so the way that I am going to run the IceStorm tools is via a front end called Appio, APIO, which I think is intended to be sort of a high-level front end to a variety of open source FPGA tools. I will link in the video description to a blog post where I describe briefly how to set it up and how to get started programming Upduino, but essentially all I need to do is do Appio build, and then Appio verify, and then Appio upload will actually upload the bit stream that was produced by the IceStorm tools to the FPGA over USB. And essentially what we should see is I have, in my constraint file, I have set the SQ_out signal to be constrained to pin 28 on the FPGA, which is this pin right here. So essentially what we should be seeing is a 6 megahertz square wave on that pin. All right, so let me do the Appio upload. And okay, so now the bit stream is being loaded onto the FPGA. Okay, and according to my multimeter, we do have about a 6 megahertz square wave being produced on that pin. I'm not sure how worried I should be that the frequency is changing slightly here. That might have something to do with the multimeter's capability of accurately detecting the edges of the signal. So I'm not so worried about that yet, but I would say as an initial experiment, this is good progress because it shows that we are programming logic into the FPGA that is generating an output on one of the output pins. All right, so here is the second experiment we're going to do with the FPGA. We are going to use a PLL phase-locked loop to multiply the internal high-speed oscillator frequency of 48 megahertz and scale it up to 240 megahertz. And actually, this will involve both multiplying and dividing the internal high-frequency oscillator frequency. So the reason that we want to do this is that the VGA mode that I would like to use, which is 800 by 600 SVGA, requires a 40 megahertz clock as essentially the fundamental timing signal that determines the correct timings of all of the other signals that will be sent to the monitor, such as the horizontal sync, the vertical sync, and the actual color signals. So 240 megahertz is a useful frequency for this mode because we can divide it by 6 to get precisely 40 megahertz. So the PLL is basically an internal special purpose logic block inside the FPGA, and the IceStorm tools provide a tool called IcePLL that will generate the appropriate configuration to produce a particular frequency. Given the input frequency of the high frequency oscillator, we can use the IcePLL tool to determine what the configuration of the PLL should be in order to generate the output frequency we want, which is 240 megahertz. So here is the call to the IcePLL tool. The input frequency is 48. The output frequency that we want is 240. And the IcePLL tool has essentially produced the appropriate configuration parameters for the PLL block to do that particular translation from the internal frequency to the external frequency. Additionally, if we use the -M option and the -F option, IcePLL will generate us a Verilog module that instantiates the PLL, and we can then use that as a module in a different part of the design. So I've already gone ahead and done that, so this is the PLL module. So now to tie everything together, here is the design that is going to use both the high-frequency oscillator and the PLL together. So here is the high-frequency oscillator module that produces an output signal, which is going to be a 48 megahertz square wave in this node called clock, and then we instantiate a PLL that takes that clock signal as input and produces an output signal called PLL clock that uses our PLL with its configuration parameters to translate that 48 megahertz internal frequency into a 240 megahertz frequency. And as before, we are just using a 16-bit counter and incrementing it on each edge of the clock, in this case the higher frequency PLL clock, and by taking bit 7 of that high frequency square wave signal, we're essentially dividing by 128, which should give us a 1.875 megahertz square wave again on pin 28, which is this pin. So when I load this new design into the FPGA, we should see the frequency displayed on the multimeter as 1.875 megahertz. All right, so once again, you know the drill. We do APIO build, then APIO verify, and then APIO upload, and hopefully we'll see 1.875 megahertz on the frequency display on the multimeter. So let's see what happens here. All right, so yeah, this is pretty close. It's a little high. Once again, I'm not sure how accurate the multimeter is at displaying the frequency here, but it's certainly very close to what we're expecting to see. So at this point, I would say we've made good progress. We're definitely programming logic into the FPGA, and we seem to be getting frequencies that will be useful for generating an 800 by 600 SVGA signal. All right, so now that we have basic control over the FPGA, let's talk a little bit about how the FPGA is going to send color information to the VGA monitor. And the way that VGA color inputs work is that they expect a voltage approximately in the range 0 to 1 volt to control the intensity of each color signal, red, green, and blue. And the voltage is sampled at a point that is connected to effectively a 75 ohm resistance to ground. So we need to design the output impedance of our circuit that generates the colors to take that 75 ohm termination into account. So the basic problem we have is that our FPGA has digital outputs that are either going to be 0 volts or 3.3 volts, and those are the only two possible states. However, we can use multiple outputs in combination to specify a range of colors. So the idea is, let's say that we have these 4 outputs, D0 through D3, that effectively will be encoding a 4-bit value ranging between 0 and 15. And we want 0 to produce essentially a 0 voltage here, and then we want 15, if all of these are on, to produce a higher voltage closer to 1 volt. So the question is, what kind of circuit do we need between the digital outputs of the FPGA and this analog input of the VGA monitor in order to get essentially a continuous or more or less continuous range of voltages here at the input? So one possible approach is to use a resistor DAC, digital to analog converter. And in particular, the type of resistor DAC that I'm showing here is a binary weighted resistor DAC. And the idea is we have this series of resistors where each one is twice the resistance of the previous. So our lowest resistance here is 450, and then 900, and then 1800, and then 3600. And the least significant bit of the output signal from the FPGA goes to the largest resistor, and the most significant bit goes to the smallest resistor. And essentially this will combine the voltages so that we get a relatively linear series of voltages at the input point here in the VGA monitor input. So now the question is, what resistor values do we pick? And I've picked these specific ones because I have determined experimentally via a simulation that these are a good set of values that will produce about the right range of voltages here at the VGA input. Okay, let me show you the simulation. Okay, so here is our simulation. I'm using the QUCS, I guess it's pronounced QUX, simulation software, and this is the circuit, and here you can see the 75 ohm termination resistor. So this is the circuit node where we want to produce a voltage in the range 0 to 1 volt. Here are our resistor values. I've used these 4 voltage sources. Right now they're all set as 3.3 volts to simulate the output pins of the FPGA, and given that they are all turned on at 3.3 volts, we should be producing something close to 1 volt here at this output node. So if I press F2, that will take me into a DC direct current simulation. And we do find that we do get about 0.78 volts, so that looks good. And just to confirm that we do get lower voltages when we turn some of these off, let's set this voltage connected to the lowest value resistor. Let's set that to 0 volts and then rerun the simulation. We should see an output voltage about half of what we saw originally, and we do get 0.367, so that's about half of our original voltage. So this looks like it should be good. So let's actually test this on the breadboard. All right, so here is our test setup. We have this 74HC125 quad buffer chip, and its inputs are driven by 4 switches in this 8-position dip switch. And essentially by turning these dip switches on and off, I can send zeros or ones to the inputs of this buffer chip, which in turn will produce digital voltages that feed into our binary weighted resistor DAC that produces then an output voltage at this point terminated by the 75 ohm resistor. And based on the combination of inputs and the combination of output voltages generated, I should get an output voltage here that I can read on our Fluke 45 multimeter here. And essentially what I'm looking for is that as I select various binary values here, I should see appropriate voltages generated, and by collecting some data, I can then put those in a spreadsheet, graph them, and make sure that I'm getting a pretty good linear series of voltages that correspond to the input values we select here. Okay, so let's give this a try. I'm going to flip the least significant bit from 0 to 1, and we should see the voltage increase. Okay, so the voltage went up to about, looks like 53 millivolts. All right, so let's turn that off and then turn the 2 on, the second least significant, and that gives us 104.8 millivolts. And then I will turn the least significant one on again. This basically corresponds to the binary value 3, and that produces 158.02 millivolts. So that's the basic idea. As I select various combinations of these dip switches, I'm essentially encoding a binary value that is then converted into an analog voltage by our resistor network here. One thing to note is that 3600 ohm and 1800 ohm resistors do exist. That's this one and this one. However, 900 and 450 are not standard values, but we can easily create them as a combination of standard resistor values. So our 900 ohm resistor is really a 750 resistor in series with a 150 ohm resistor, and similarly, the 450 ohm resistor is really a 300 plus a 150. All right, so I will collect some data and then show you the results. Okay, so here's the data I collected from this experimental setup with each of the 16 possible digital values that we can produce and the corresponding analog voltages that we measured. And this seems pretty good. That looks pretty flat. There's definitely a little bit of a discontinuity when we go from 7 to 8, but overall, I think this is going to be fine. As Dave Jones would say, good enough for Australia. All right, so it turns out that I was a little bit confused about the proper voltage levels for these VGA color signals. I thought they could go from 0 to 1 volt. It turns out, at least depending on which source you consult, that the correct maximum voltage is actually 0.7 volts. So our resistor DAC produces a voltage that's slightly above 0.7 volts when we are at maximum intensity. I don't think this is going to cause any damage to the monitor, but it might mean that we get oversaturation with more intense color values, and that's not necessarily a big deal. If I really wanted to fix this, I could either change the resistor values or potentially put a diode in series with the digital outputs in order to drop the digital voltage a little bit in order to constrain the analog voltage of the mixed color signal to be in the right value. But as I said, I don't think this is actually going to be a big deal in practice. All right, so you may remember that in our initial experiments generating square waves from the FPGA, we were having trouble getting a solid frequency output from the FPGA. It kind of was a little bit too high and the frequency sort of varied. So I am now working on generating synchronization signals for the VGA monitor, and right now I'm trying an experiment to generate horizontal sync, and the horizontal sync frequency for the 800 by 600 60 Hz SVGA mode should be precisely 37.8787 kilohertz. So of course, what you can notice on the oscilloscope here is that we are getting a little over 38 kilohertz, and also, disconcertingly, the frequency is changing slightly. So there is some significant jitter in the timing generated by the FPGA, and that's not good for generating video where we want our synchronization pulses to be absolutely rock solid. So we need to investigate why we are not getting accurate timing out of our FPGA. So the good news is I know why we are getting this inaccurate timing, and I also know how to fix it. So let's do a couple experiments to show how we can get reliable timing signals out of the FPGA. Alright, so here's the Verilog file for our initial experiment where we divided the internal high-frequency oscillator of 48 megahertz by 8 to get a 6 megahertz square wave, and as we can see, we aren't getting exactly 6 megahertz, and the frequency is sort of changing. So the problem is actually the internal high-frequency oscillator. So the convenience that is provided by the internal high-frequency oscillator is that it's built into the FPGA, but the downside is that it has a lot of jitter and it's not terribly accurate. So what we are going to do is take advantage of the fact that the Upduino 3 board has an onboard 12 megahertz oscillator. And what we can do is route that oscillator signal, which appears on this pin. It's actually labeled ground on the silk screen, but the silk screen is wrong. This is a 12 megahertz output. We will connect that to GPIO pin 20, which is one of the global clock inputs, and then we will use that 12 megahertz frequency as the basis for driving the Verilog design. So this is the updated design file, and we are taking the external oscillator signal on an input. The constraint file has that as pin 20. And we are also feeding that external oscillator signal through a global clock buffer. So a clock buffer is essentially dedicated hardware on the FPGA, which helps to distribute a clock signal accurately to all parts of the hardware inside the FPGA. That's actually quite important because it eliminates things like skew. All right, so let's see if this will work. So APIO build, APIO verify, APIO upload. All right, let's see what happens here. Okay, good. So we have exactly 6 megahertz now, and as you can see, it is a steady 6 megahertz. We're not getting the jitter that we had before, so that's good progress. I should note quickly that the reason that we are getting 6 megahertz from our 12 megahertz external oscillator signal is that we're dividing it by 2. Our original 48 megahertz signal was divided by 8 to get 6. Now we have a 12 megahertz signal that's being divided by 2 to get 6 megahertz. The next experiment we're going to do is to make sure that we can still use our PLL to translate the base clock frequency to the 240 megahertz clock frequency that we'd like to use as the main clock for the VGA output. And in this case, we need to adjust the PLL parameters slightly because now we are converting a 12 megahertz signal to 240 megahertz signal. So this is the updated PLL configuration, once again generated by the ICE PLL tool. So the setup here is that the external oscillator signal goes into the PLL, and then the output of the PLL goes into the global clock buffer, which then drives the incrementing of this counter. And again, by dividing it by 128, we should convert the internal 240 megahertz clock to a 1.875 megahertz clock that appears on our output pin. So let's see if that is going to work. So APIO build, APIO verify, and then of course APIO upload. Okay, so now we can see 1.875 megahertz exactly, doesn't change, doesn't fluctuate. It's exactly the output that we expect. So this is really good news. We now have accurate timing for our design. All right, so the next thing we need to tackle is the generation of the horizontal and vertical sync signals for our VGA output. All right, so let's talk about how VGA signals are actually generated. So I've drawn this diagram, and the idea is that the display processor is going to be generating signals starting up here, and then it will generate one row, and then it will move to the next row and generate that row, and then generate the next row, and so on and so forth. And within each row, there are a bunch of instants in which a pixel could be generated. However, not all of the time positions in the signal actually represent visible pixels. The visible pixels are only a subset of all of the pixels being generated. So let's first talk about the horizontal timing. And as you can see, each row that is generated consists of 4 distinct regions: the back porch, the visible region, the front porch, and the sync region. And essentially, these are just a particular number of pixel times in each area. So for example, if this is the 800 by 600 SVGA video mode, the visible part of each line will consist of exactly 800 pixel times. So the back porch and the front porch, essentially nothing is going on during those times. No colors are generated and no sync information is generated. In the sync region, the horizontal sync signal, the H-sync signal, is going to have a pulse, and that is essentially what allows the monitor to synchronize on the horizontal part of the signal. And the 800 by 600 video mode has a positive sync pulse, so the H-sync signal is normally low, but then we generate a positive pulse when we are within the sync area of the row. The vertical timing is similar in concept to the horizontal timing. There is a back porch, a visible region, a front porch, and a sync pulse. But now we are counting rows rather than columns. So again, the back porch and the front porch, nothing is really happening. The visible region is where the video is actually generated. And again, in the sync pulse, when the row is one of the rows that is part of the sync, then again, we are going to generate a positive going pulse, again because the 800 by 600 mode has a positive sync signal. So from the standpoint of generating these sync signals and also the color signals from the FPGA, the idea is that we're just going to have counters that count which column we're in and which row we're in, and that's how the FPGA will know whether to generate sync pulses and whether to generate a color signal. So basically all we have to do is generate these signals over and over again once per frame, and that's how our video signal is generated. Alright, so let's go ahead and look at the Verilog code that is going to generate the sync signals and the color signals. Alright, so here's our Verilog for generating our SVGA output. So now the main module has output registers for VSync and HSync, and also 4-bit registers each for red, green, and blue color signals. We have the same code as before that is going to take our 12 MHz external oscillator signal, use a PLL to increase it to 240 MHz, and then use a global clock buffer to distribute it to the rest of the design. Because our clock is 240 MHz, but the SVGA 800 by 600 timing is based on a 40 MHz signal, we have this 3-bit register called tick, which repeatedly counts from 0 to 5 and then repeats, and that's essentially how we divide that 240 MHz signal by 6 in order to produce a 40 MHz signal. There is a fairly straightforward state machine for generating the horizontal timings, and essentially what I've done is just created some constants that indicates at which pixel in a row each region ends. And notice that I've slightly reordered the regions. I actually have the visible region first, then the front porch, then the sync pulse, then the back porch. It actually doesn't matter what order the regions are in as long as the relative order is preserved. Our horizontal state machine is driven by this H-count register, which simply counts up the pixel position in each row from 0 to the maximum. And the state machine for generating the horizontal sync is whenever tick is 0, and that happens 1 out of every 6 times, and that's how we divide, again, the 240 MHz clock into a 40 MHz clock. We check to see what the current H-count value is, and depending whether we have reached a threshold between regions, we either turn on the sync signal or turn off the sync signal, and we either increment the horizontal count or reset the horizontal count. The state machine for generating vertical sync is very similar to the one for generating horizontal sync. The main difference is that we only update the vertical sync signals when we reach the end of a line. Finally, this is the code that generates the pixel colors, and mainly what it needs to do is check to see whether H-count and V-count indicate that we're in the visible region. If so, we generate a solid pixel color. Otherwise, we just generate 0 because we don't want to generate color when we're not in the visible region. One of the big advantages to putting the visible region before the front porch, sync, and back porch in the state machines that generate the horizontal and vertical sync is it means that the H-count and V-count registers contain the exact pixel column and row, and that's going to be useful when we finally reach the point where we're generating actual text or graphics. Alright, so here's our test setup. Here's the Upduino board. This board is our resistor DAC for the red, green, and blue color signals that are 4 bits each as they come out of the FPGA, but then they're mixed together to produce our analog color voltages, and then these pins produce the H-sync and V-sync signals. The color signals and the sync signals are going to this VGA breakout board. It's not connected to a monitor right now. I just want to test to see if the signals that we're generating look right. Alright, so what I'm going to do is I am going to show the H-sync and V-sync and the blue color voltages on the oscilloscope, and the triggering is set that we will trigger on the vertical sync, and essentially we'll see the horizontal sync and the color signal relative to the vertical sync. Alright, so let me upload the design into the FPGA. Okay, so here we go. So here we can see a vertical sync pulse. And so here are the horizontal sync pulses, and obviously they occur much more frequently than vertical sync. So here is the front porch and the vertical sync, and the back porch for the vertical sync. And as you can see, when we generate these color voltages, we are only generating a positive voltage at points where we are in a visible region. So for example, here, these dots where we have 0 volts, those correspond to horizontal sync pulses, and of course the front porch and back porch of the horizontal sync being generated. So I would say at this point, this looks quite promising. I think this is more or less what we are expecting to see. So at this point, I think we are ready to try this on an actual VGA monitor. So one thing I should mention is that these VSync and HSync signals are 5-volt TTL signals, so we can directly connect the 3.3 volt outputs of the FPGA to those inputs on the monitor. We don't need to do any kind of level conversion or attenuation. Alright, so here we are for the moment of truth. I have the VGA output of our circuit hooked up to this little IBM point of sale monitor, which is actually a good choice for this experiment because it actually has 800 by 600 native resolution, and you would figure if anyone can make a VGA compatible monitor, it's probably IBM. So let me go ahead and program our design into the FPGA. Here it comes. Perfect. So this sort of bluish purple color is exactly the right color based on the color values that we are generating from the digital outputs of the FPGA. So this is fantastic. We are absolutely generating valid 800 by 600 video. All right, so for the next and final test, I would like to generate a test pattern that shows a wider range of colors and also some intensity gradients, and that should give us a good sense of whether we need to make any adjustments to our resistor DAC or whether it's okay the way it is. Okay, so I have updated the Verilog, and there will be a design that will show some horizontal color gradients with different colors sort of as we go down the screen. It's not terribly complicated, but it should give us a good sense of how well we are doing with the colors produced by the resistor DAC, so let me program that. Okay, so here we go, and this honestly looks really good. So the top line is sort of a gradient, but it's based on black, so everything's black, but we have a blue, green, cyan, red, magenta, yellow, and white gradient. And basically what you can see here is the various color steps from 0 intensity to 16 intensity. And what's sort of interesting and encouraging is that there is a distinct difference between step 14 and step 15, the second most intense and the most intense. And given that we were a little uncertain about whether we had a correct range of color voltages, this actually looks fantastic. And I would say this looks pretty linear. You know, I do think between 7 and 8, there's probably a little bit more of a difference than there should be. But overall, this is actually much better than I was assuming it would be. This looks fantastic. So I think we have made really excellent progress on generating 800 by 600 SVGA. And now the interesting part of the project begins, where we actually have to be able to store fonts and frame buffers and actually render graphics. But that will come in a future video. All right, well, that was quite an adventure, but I think we made some very nice progress in getting our FPGA, at least in the initial stages of generating a VGA signal. So the next steps for the display processor are to interface the display processor to the host system so that the host system can send it commands and can eventually send it data to display. The first thing I would like to work on in terms of an actual display is basically a text mode, so I need a way to upload fonts and then put text in the video memory and have it rendered. In other aspects of the system design, I have a new PCB design for the CPU and glue logic board, so I'm going to be making a video about that in the near future. So stay tuned, and I will see you in the next video.